welcome to day 2 of your challenge. If you guessed that the reaction was an E1 reaction, you are correct. Let's do a general mechanism and start filling the top of our reaction sheet in for an E1 reaction. So for an E1 reaction, it's similar to this SN1. We have to have a leaving group, and that leaving group is going to leave, and then we're going to form our carbocation. Remember that this carbocation needs to be stabilized, or in this case, it's a tertiary, so stabilized by resonance or highly substituted. Then we're going to have some base. Many times it's our leaving group, sometimes it's something else in the reaction, and we'll go over a specific example, and it's going to deprotonate right beside the carbocation, and these electrons are going to fall down to make our desired alkene. The way you want to think about this is E1 elimination, and it's unimolecular, okay? Our rate determining step is here, forming this carbocation. So for your day 2 challenge, we had 2-pentanol and we had sulfuric acid, and this reaction was heated. Now when you look at this, you again don't have a leaving group. This OH can't leave, but we can turn it into a good leaving group. So we're going to protonate, doing an acid-base reaction with our sulfuric acid. Let's draw what we have from here. We just made this OH group into water here, which is a great leaving group. So now we're going to have our leaving group leave. Let's draw the conjugate base of our sulfuric acid. Now remember that this is not nucleophilic, so these non-nucleophilic acids are great for E1 because we're trying to make an alkene. Let's now draw our carbocation that formed here. And what we're going to be doing is, because an E1 reaction is reversible, we're drawing the thermodynamically most stable product. So we're going to be picking a proton here from the inner side. We're going to be making the most substituted alkene, which is the most stable product. We're going to take water, which was formed after we made it leave, and we're going to deprotonate and form our desired alkene. Now, I've drawn here a trans alkene. It's trans because the 2 alkyl groups are opposite of each other. This is the most stable, but you'll also form some of the cis alkene, in which both of your groups are on the same side. The trans is more stable because the 2 groups are opposite of each other. There's less steric clash, so this is typically the major, and it's the most substituted, thermodynamically stable product here. Now let's get into the bottom part of your reaction sheet. Okay, now when we think about an E1 reaction and stereochemistry, remember that the alkenes that we're making, they do have 2 stereocenters here. They're not chiral, they're not asymmetric chiral carbons, but we can orient them to have a difference in spatial orientation of the groups, trans versus cis. So in stereochemistry, we're going to list here that trans is favored over cis. For the regioselectivity, remember we're thinking about constitutional isomers and what can form from this reaction. And we know that the most substituted alkene will form. And we also still have to be aware of the carbocation rearrangements. So from secondary carbocations rearranging to the tertiary carbocations. You might find yourself making more notes about this carbocation rearrangement. Maybe write down an example of a carbocation rearrangement to help remember this. Now for solvent, this is polar protic, but in particular, like in the example I showed before, one of the most useful ways to use an E1 reaction is that dehydration reaction. I talked about using that 2-pentanol in our example. So you might also want to write that typically we're using non-nucleophilic acids, so strong acids that are non-nucleophilic. I'm going to write NUC for nucleophilic. And here for the notes section, this is where you can write whatever your heart desires. But a couple notes, these are really similar to SN1 reactions, where one, we need a good leaving group. In this case, we made water as a good leaving group, but you could also think about bromine or iodine. Now, another side note is this competes with SN1. And you're always going to get a mixture of products unless you're doing the dehydration that we talked about with that strong acid in the presence of an alcohol. Another thing you might want to write on your notes is this carbocation. Same principle as the SN1 reaction, where tertiary is more stable than secondary, which primary doesn't form, and absolutely no methyl carbocations. And the last one, you might want to put down some very specifics about what you could use for your reagents in your E1 reaction. You can think about different strong acids or phosphoric acid. Let's discuss some about this E1 versus SN1 competition. First off, E1 reactions, we make an alkene. And I remember that because an alkene has those two E's in it. So that's how it reminds me that it's an elimination reaction. And then another thing I want to highlight is that, especially for these reactions with alcohols, the type of acid we use is very important. Here we use this non-nucleophilic acid. Let's go over this H2SO4 example that we had before, and I showed you this conjugate base of sulfuric acid. And what you'll notice here is that this oxygen, although it kind of looks nucleophilic, it really isn't, because this oxygen is sharing this negative charge through resonance throughout this compound. Now, this anion has this delocalized negative charge. So this non-nucleophilic strong acid is especially important because there's no nucleophile present, so you wouldn't get any SN1 chemistry. Whereas if you wanted SN1 chemistry and you started with an alcohol, like our day one challenge, you would want to use an acid that makes a nucleophile. So this HBr, okay, would make H plus as well as Br minus. And we know that Br minus can be a nucleophile. But this sulfuric acid conjugate base cannot be a nucleophile. So that's kind of one of the ways we can differentiate between E1 and SN1 reactions. Again, use the notes section as a way for you to remember. As you go through practice problems, you're going to find little things you want to add to your reaction sheet. This is a way you can compile what you've learned so you have it all on one sheet. So that's it for the E1 reaction sheet. Congrats on making it to day 2. Let me know in the comments below what you put on your reaction sheet. This is going to help other people as well as we go through this. All right, I will see you tomorrow for our day 3 challenge and our 3rd reaction sheet that we'll go through together. All right, see you soon.